All right, so let's get started here. This week we're going to be talking about, actually for the next 2 weeks really, we're going to be talking about chemical reactions. We're going to look at a bunch of different reactions. We're going to talk about reaction categories, interpret, what's going on in these chemical reactions. Importantly, what's going to be missing from our discussion of chemical reactions is why these chemical reactions occur. Okay, and that's because that is one of the most difficult questions that you can ask in chemistry, is why a particular chemical reaction occurs. It turns out that that question is really this gigantic, ugly math problem involving math that is far more complicated than we've ever done in our lives at this point, right? What's called quantum mechanics. And the bottom line is that question of why is really, really difficult, okay? So I know one thing that I got hung up on as an instructor was going through these reactions is like, well, why does that occur? To put that out of your mind, okay? We're going to focus on what it is that's occurring, okay? And sort of how we illustrate that using these chemical equations. And we discussed those a little bit last time, specifically with balancing those chemical equations, and we're going to kind of build off that here today, all right? So what we can observe is that if we take sodium and we mix it with chlorine, it will produce solid sodium chloride. So our goal is to take this phrase right here and to turn it into one of those chemical equations. All right, so this is telling me that sodium all by itself, right? So that would be Na is my symbol for sodium off my periodic table. I'm going to combine that with chlorine. So sodium with chlorine. And this is going to produce, so now I'm going to do my arrow here and do my product side, my sodium chloride. All right? And now I have this ionic compound, so I have to look at the charges of these ions. A sodium ion has a +1 charge. A chloride ion has a -1 charge. So sodium chloride would be NaCl. Okay? So we have these two components here. Our reactants are the sodium and the chlorine, and our product is this ionic compound, the sodium chloride. And we talked a lot about these ionic compounds, how we go from name to formula, or we can go from the formula to the name, all right? Let's look at the other two components here, because we've talked a lot about how we turn sodium chloride into NaCl here. But what about the sodium and the chlorine, right? In my phrase here, it's saying sodium, so all by itself, right, is mixed with chlorine, so all by itself, not in a compound with anything else. These would be elements in what we would call their standard state, all right, all by themselves. Okay, when I did my formula for sodium all by itself, that was Na, right, the symbol from the periodic table. When I did my formula for chlorine, though, it's Cl2. There's this 2 down here, okay? So where does that come from? It turns out that chlorine is one of a few elements that in their standard state are what are referred to as diatomic elements, all right? So we're going to look at our periodic table here. Okay, again, chlorine is one of a few elements that are called diatomic elements. Okay, these are elements whose atoms always appear in pairs in their standard states. Okay, so this name diatomic, if we're going to pick it apart here, what do we think the di means? 2. And so these are 2 atom elements. They always appear in pairs. Okay? So we got a short list of our diatomic elements here. All right? Hydrogen always appears in pairs, H2. Same thing with nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Okay, so we have this list of 7 elements that are diatomic elements. So if I tell you that fluorine is involved in a reaction, you know I'm talking about F2 because it's one of those diatomic elements. Okay? Now to be clear, this is only when it's in its standard state. As soon as I start pairing these up and making compounds like sodium chloride, it's not NaCl2, right? This is only for elements in their standard state. When they're all by themselves, they appear in pairs. Okay? So this list here we just got to know. All right? I think it's the easiest thing to do is to look on our periodic table. We have 7 of these diatomic elements. It turns out that they make a little 7 on the periodic table. But if I count, there's only 6 in that 7. The missing one, this oddball, hydrogen over here, right? So these are our 7 diatomic elements. If we're ever talking about oxygen all by itself, the oxygen that we're breathing in right now to survive is diatomic oxygen gas, O2. All right? The nitrogen, which is actually the main component of air, is N2, 2 nitrogen atoms paired up together. All right? So there are certain elements that we just got to know in their standard state are diatomic elements. So when I said in my reaction here that sodium was combined with chlorine, I know sodium's not one of my diatomic elements, so that's why I just have Na all by itself. But chlorine is one of my diatomic elements, so when I write the formula for chlorine, it's Cl2. Okay? What we did talk about with these chemical equations as well was the balancing. The balancing component's really, really important. That's how we use these quantitatively. We'll do that next class. All right, but in this chemical equation right here, if I'm going to balance, I'm going to keep track of my sodiums on both sides and my chlorines on both sides. Right now, on my reactant side, I have 1 sodium and 2 chlorines. On my product side, I only have 1 of each, so my chlorines are imbalanced. Everybody take a second and balance this chemical equation here. So if I put a 2 out front of my sodium chloride, that will balance my chlorines, but now my sodiums are out of balance, so I got to jump back to the reactant side, put a 2 out front there. Okay, so now I have this balanced chemical equation. There's one other thing that's missing from this chemical equation that we haven't discussed yet. Okay, and that is what's called the states of matter. Okay? So in my problem, my compound, my sodium chloride, it told me was a solid, right? And we don't know what the state of matter is for just a random compound. I mean, some of them we know because, we've experienced it. CO2 we know is a gas. But in general, you have to be told these things. There's no way to really look at a formula and know what the state of matter is. I will say ionic compounds are solids at room temperature. Covalent compounds, it's really sort of any game. It could be a gas, a liquid, a solid, okay? So how this is going to appear in my chemical equation here is my solid sodium chloride. I'm going to put this little S next to the formula for sodium chloride to indicate that it is a solid. Okay, so what we're going to do is we're going to build into this formula here, into our chemical equation, the states of matter of these compounds. So let's first take a step back and talk about these different states of matter. Okay, these are something that you have sort of a intuition about because you encounter solids and liquids and gases all the time in your life, but we haven't really formally laid it out here. All right, so in the world of chemistry, all of this matter can exist in one of 3 phases. We can have a solid, a liquid, or a gas. Okay? So the difference between these phases of matter are are the interactions that are occurring between neighboring molecules, right? So let's think of water, because we've all seen water in all three of these phases before. We know ice is water in its solid phase. Water in my water bottle right here is in its liquid phase, and when we boil it and it generates steam, that would be water in the gas phase. Okay? So the big difference between these three phases of matter are the neighboring water molecules, right? What's going on between neighboring water molecules? Okay? So if we were to hop into our magic school bus and shrink on down to the atomic level and look at what's going on in these three phases of matter, so this is what we would call a microscopic view here, right? We're really, really tiny. Okay? We would see that neighboring molecules in both solids and liquids are very close together. Okay, so this is one of these distinguishing factors of these phases of matter, is neighboring molecules in both solids and liquids are really close together. They're hugging one another, right? Everybody's kind of stacked on top of each other in both a solid and a liquid. And in a gas, that is very, very different. Now these molecules have separated from one another. They're no longer talking to one another. They're kind of flying around independent of their neighbors, right? So in terms of my neighboring molecules in the gas phase, they are very far apart from one another. Okay? So one of the distinguishing factors between solids and liquids, both of them, neighboring water molecules, for example, are very close together. The difference is in a solid, your position is fixed. So your neighbor is not changing, right? Whoever you got frozen next to, you're going to be frozen next to them for the rest of time. Okay? So neighboring water molecules in solids are close together, and they do not change. In liquids, these water molecules are also very close together. The difference is that they're tumbling around one another, flipping around throughout this bottle right here, constantly changing their position, right? So in a liquid, these molecules are on the move. They're kind of dancing around within that container. They're still right up against their neighboring water molecules, but whoever their neighbor is at this moment in time, it's going to be different in a few seconds, right? Because those neighbors are constantly changing. And then in a gas, your neighbors are so far apart you don't even see them, right? But the bottom line is the position is no longer fixed. It's bouncing around this container. So again, we would say that our neighbors are changing here, but we can note that they're really far apart, right? So the bottom line is in liquids and gases, our molecules are on the move, okay? Importantly, in a solid, your molecules are actually also still moving, but they're kind of like vibrating in place. It turns out that molecules are always on the move, unless you're at absolute zero, the coldest possible temperature. There's always some amount of movement of those molecules. All right, but even though they're kind of vibrating in place, their neighbors don't change here. Okay, so this is what we would see if we shrunk down on a microscopic scale regarding these different phases. If we look on a more macroscopic scale, right, so this is what we would see with our eyeballs here. Okay, these phases also behave very differently. Solids have a fixed shape. Right, so when you freeze ice into that little cube form and you pop it out of the mold, it's still a cube. Right? So they have a fixed shape. If you take it and you put it into a glass, it doesn't change its shape. It's still in that cube form. Right? They also have a fixed volume. Right? So if your ice cube was a milliliter big and you take it and you put it in a glass, it still has that same volume. It doesn't change its volume. Okay? A liquid also has a fixed volume. If you think of how a recipe works, when you go and you measure out a cup of water and you take it over and you pour it into the bowl, it doesn't stop being a cup of water. You've got that fixed volume for your liquid. Okay? The big difference is that a liquid will take the shape of whatever container that it's placed in. Right? So a liquid does not have a fixed shape, it has a variable shape. If you take that cup of water and you put it into a bigger glass, it's going to take the shape of that glass. If you spill it on the floor, it's going to spread itself out all across, right? So although that volume is fixed, your cup is still a cup, it's going to take the shape of whatever container you put it in. All right? A gas also has a variable shape. It will take the shape of whatever container you put it in. All right, the big difference about a gas is it will also expand or contract to completely fill whatever container it's put in, right? So the volume of a gas will change depending on what container it's in. So not only does it have a variable shape, it also has a variable volume. All right, so we have these three phases of matter here. They differ both in terms of what we would see if we shrunk down on the microscopic scale, but also on the macroscopic scale with regard to their shape and their volume. Okay? Now, importantly, we were talking about elements in their standard state. We talked about which elements were diatomic. The other thing that we should be able to do is to determine the state of matter of an element in its standard state. Okay? And for this, we're going to use our periodic table on the board here. This is a little bit of a cheat sheet, the one on the wall here. If you notice, there's this different coloring scheme that you see. Certain elements are in black, certain elements are in red, certain elements are in white. There's actually two up there that's kind of hard to see that are in blue. Okay? These correspond to the different states of matter of those elements in their standard state. So, let's start with the easy one here because we have a special name for that last column all the way on the right-hand side there. That is the what? The noble gases, right? So the red on our periodic table here, all of these elements that are listed in red are gases in their standard state. Okay? And since we don't have this little cheat sheet periodic table on our exams, I'm going to update our periodic table here to include that state of matter information. I don't feel like this is something we need to have memorized here. We do need to be able to look at the periodic table and figure out the state of matter of an element. Okay? All right, so we have all these elements here that are in red. And again, red is our gases. There are two elements up there that are in blue. Can anybody spy them? Bromine's one of them. And the other one is Hg. Yep, mercury. Okay? There are only two of them. These are the two that are liquids in their standard state. All right? All the other elements up there, the ones in black, are our solids in their standard state. All right, now, if you look, you'll notice that towards the bottom of the periodic table, there are some that are outlined in white there. What the heck does that mean? These are the man-made elements, and so we don't really know their states of matter. They don't really have states of matter. They were created in a lab. Oftentimes, they are unstable, and so they existed for like 5 milliseconds, so somebody could write it down in the record books that it existed, but they're not elements that are occurring in nature that we're doing chemical reactions with. Okay? So, bottom line is by looking at our periodic table, we can determine whether an element in its standard state is a solid, a liquid, or a gas. And we need to update our chemical equation to include that information. Okay? So we said that the S stands for solid, like we did over here for our compound, sodium chloride. We're going to use an L if our compound is a liquid. And what do you think we're going to use if our compound's a gas? A G. We're really creative. All right, so let's update our chemical equation here to include this information. Sodium all by itself, so it's in its standard state, I know is a solid according to my periodic table. All right, and you will see that all of our metals are solids in their standard state. All right, what about chlorine? What should I update my chlorine with here? Chlorine is a gas. It's in red on our periodic table, so it gets that little G next to it. So here we have a complete chemical equation. All right, we have our symbols of our reactants and our products. We have our balancing going on. I have the same number of sodiums on both sides and chlorines on both sides. And then lastly, we have the state of matter information as well. All right, again, for any sort of a compound, you would have to be told what the state of matter is. It'll be built into the problem, solid sodium chloride, okay? But for these elements that are in their standard state, we should be able to fill in that information based on our periodic table here. All right, so let's do another one from scratch here. So solid aluminum oxide decomposes into aluminum and oxygen. All right, take that phrase and build me a balanced chemical equation. All right, so I need to take my name for my ionic compound here, the aluminum oxide, and I need to turn it into a formula here. And remember, when we're building these formulas, it's all about the charges, right? So I'm going to write down each of these ions with their charges. The aluminum ion has a +3 charge. The oxide ion has a -2 charge. So I'm going to do my swappy swap method here, and I get my formula Al2O3. And my state of matter of my aluminum oxide? Solid, because it told me in the problem, right? It said solid aluminum oxide. So now this is going to decompose into aluminum and oxygen, these two elements all by itself. So now I have these elements in their standard states, okay? Aluminum is just Al, but oxygen is what? What do I need to do to finish off my formula here? O2, it's one of those diatomic elements, right? One of those 7 diatomic elements we just got to know. Lastly, I need to fill in my states of matter for these elements. Aluminum, being one of our metals, is a solid, but oxygen at room temperature is going to be a gas, right? It appears in red on our periodic table. And then I'm done? Now, last step is very, very important, is the balancing step. And we'll see next class why we need these balanced chemical equations. Okay? Let me make a little bit more room for myself. So I need to keep track of the aluminum on both sides and the oxygen on both sides. I have 2 aluminums on my reactant side and 3 oxygens from my formula. And I just have 1 aluminum on my product side and 2 oxygens. Okay? If we look at our oxygens in particular, we have a little bit of a tricky situation on our hands because there's no way for me to turn this 2 into a 3. So instead, I'm going to turn them both into their least common multiple here. So if I take my oxygen, my O2 gas, and I multiply that by 3, that would give me a total of 6. And if I take my aluminum oxide and I multiply it by 2, that would give me a total of 6, right? So 3 and 2 have no common factors, so instead we got to turn them both into their least common multiple. When I put that 2 out front of my aluminum oxide, I change the number of aluminums I have. Now I have a total of 4 on my reactant side, so I can balance that out with a 4 on my product side. All right, so balancing that chemical equation, now we have this complete chemical equation here. Okay, so we took this description of our chemical reaction and turned it into one of these balanced chemical equations. All right, another thing that I could ask you that we're going to learn about this chemical equation right here is to look at it and put it into a particular category. All right, so we have 2 different examples here. So let's talk about categories of chemical reactions. In our first example here, we were taking sodium and chlorine and we were combining them together to make this product, sodium chloride. This is what would be called a combination reaction. Okay, so a combination reaction. Also called synthesis reactions, especially in organic chemistry. Okay, this is any time we have multiple reactants coming together to make a single product. All right, so a combination, given a balanced chemical equation, we can classify it as a combination reaction if we have multiple reactants and just one product, right? Those reactants are combining together to make that product. Okay, in our the last example we did, this was the exact opposite. Now we have a single reactant that's decomposing into multiple products. This is what we would call a decomposition reaction. Okay, sort of the inverse of a combination reaction. This is when we have a single reactant that's breaking apart into multiple products. All right, our next category is what's called a single replacement reaction. Okay, and this one's a little bit trickier to see, so I'm going to use some color coding here to represent these different elements. So we have one thing all by itself, and it's going to react with a compound. And what we're going to see is the A and the B are going to switch places in this reaction. So on my product side, now I have B all by itself, and A is paired with C. Okay. Let's look at an example of this type of reaction here, but the first thing that we need to do is we actually need to update our states of matter here to include one more. It's not technically a state of matter, but it is a form in which we see chemical reactions occurring a lot, and that is what's called an aqueous solution. Okay, so a solution, and we'll talk a lot about solutions next week, but this is what you get if you, a solution is what you get if you dissolve a compound in water. Really, you could dissolve it in any liquid, but if you're talking about an aqueous solution, you're specifically talking about dissolving that compound in water. All right. This is a really important form in which chemistry happens. We are all essentially just bags of aqueous solutions, right? Our cells, our blood, everything that we have is a solution, this water-based solution, and there's a lot of chemistry that happens in solution. All right, so this is a really popular method for carrying out reactions is in an aqueous solution. And I will say both of those words are key words here. If you see just aqueous or you see just solution, you're talking about an AQ here, designation for your compound. All right, so let's take a look at one of these. We're going to, again, build a balanced chemical equation here. So it turns out that if you take copper and you put it in a solution of zinc chloride, that strip of copper is actually going to dissolve into that solution, producing solid zinc. And aqueous copper to chloride. All right, so take this and turn this into our balanced chemical equation here. All right, I'm going to give you all a head start, and then I'm going to quietly sort of go in here and fill in so you can look up if you're stuck. right, so we have our copper all by itself. So that's going to be copper in its standard state, which is a solid. That is put into a solution of zinc chloride, right? And that word solution is how I know that this is an aqueous compound here. All right? Remember, zinc is one of those transition metals, but it's a special transition metal. It always forms a +2 ion. So when I do my formula here for my zinc and my chloride, and I do my swap, I get ZnCl2. All right, remember there were 3 such examples of these, and let's just go back to our periodic table because they kind of sat next to each other. All right, so those exceptions that we got to know, we actually already did one of them, aluminum. Aluminum has a +3 charge. Zinc always has a +2 charge. And silver always has a +1 charge. So these were metals that we just had to know their charge, even though they weren't in one of these first 2 rows here. All right, so I have my aqueous zinc chloride being mixed with copper metal, and this is going to produce zinc. So now the zinc is all by itself. So I have zinc in its standard state, that solid zinc. And copper 2 chloride, remember that 2 is telling me the charge on the copper ion. I know my chloride ion charge based on where it lives on the periodic table. So when I do my swap method here, I get CuCl2. And again, my problem told me that this was aqueous copper 2 chloride. So that's why I have that AQ designation in my name. Okay? And then luck has it that this equation is already balanced with these 1, 1, 1 coefficients here. I got the same number of coppers on both sides, the same number of zincs on both sides, and the same number of chlorines on both sides. So in terms of balancing, I'm just going to leave all those coefficients as 1. All right, and again, this was our example of a single replacement reaction. So let me just use some color coding here so we can prove to ourselves that it fits that sort of formula that we laid out on the previous page here. I have copper all by itself, and then the zinc is paired with the chlorine. If I use this same color coding on the other side, you can see that the copper and the zinc have switched places here, right? Copper goes from being all by itself, and zinc it is in a compound with chlorine, and now they've swapped. Now zinc's all by itself, and copper is in a compound with chlorine. So this would again be an example of a single replacement reaction. Okay, so how did I know this reaction occurred? I just know. You guys are going to trust me. Right? There are going to be, at some point, we're going to build up to some reactions that we can actually predict the products of. For right now, that's not the name of the game, right? The name of the game is being able to interpret this information right here and turn it into these complete balanced chemical equations. All right, so there's one more category of reaction that we're going to cover. These are what are called double displacement. Okay, again, I'm going to use some color coding here. So now we have 2 compounds. All right, we have A paired with B and C paired with D, right? So we have these 2 compounds. And what's going to happen is A and C are going to swap places. Okay, so on my product side, now I'm going to have C paired with B, and I'm going to have A paired with D. Okay, so an example of this type of reaction here, and we're going to talk a lot about these next week. Okay, but these are what are called precipitation reactions. We're going to take two solutions and mix them together, and a solid is going to form and crash out of that solution. All right, so if we take aqueous silver nitrate is mixed with a solution of sodium chloride, it produces solid silver chloride and aqueous sodium nitrate. All right, so silver nitrate. Nitrate is one of those polyatomic ions that we just got to know the formula for. NO3 with a -1 charge. The silver ion has a +1 charge, so when I put those together, I get AgNO3. And my problem told me that this was aqueous, so I have that AQ designation here. Sodium chloride, same thing. I mean, at this point, I think we know sodium chloride, but nonetheless, how we got that formula is based on the charges of the sodium ion and the chloride ion. And again, in my problem, it said that this was a solution of sodium chloride, so again, gets that AQ designation, right? It can say either aqueous or solution. Both of those are telling you the same thing. This produces solid silver chloride. So now I have my silver ion and my chloride ion. When I pair those together, I get AgCl. And again, my problem told me that this was a solid that was produced here. And then I'm also left with aqueous sodium nitrate, right? So my Na plus NO3 minus 1, right? Pair those up, I would get NaNO3. And again, it told me it was aqueous sodium nitrate, so that's why I have that AQ designation. Okay? And again, this is an example of what we call a double displacement reaction. So if I use my color coding here for my silvers on both sides and my nitrates on both sides, my sodiums and my chlorides, okay? You can see that the silver and the sodium have swapped positions, right? My silver was paired with my nitrate, my sodium was paired with my chloride on the reactant side, and now they've swapped. My cations have swapped position. Now it's silver with the chloride and sodium with the nitrate. All right? Cool. All right, we're going to build off this next class.